Imagine this for a second. What if a tiny chip, thinner than a human hair, could sit gently on your brain and help it communicate directly with machines? That is exactly what researchers at Columbia University are working on right now, alongside teams from Stanford, the University of Pennsylvania, and New York Presbyterian Hospital. Together, they are building something that feels like it belongs in science fiction, but is very much real. This device is called the Biological Interface System to Cortex, or BISC for short. From above, it looks about the size of a postage stamp, but its actual volume is incredibly small, only a few cubic millimeters. Engineers managed to shrink it down to just 50 micrometers thick, which makes it flexible enough to bend and naturally follow the curves of the brain instead of pressing against it. When it is implanted, surgeons do not push it deep into the brain. They make a small opening in the skull and gently slide the chip between the brain and its protective lining. It rests right on the surface, which is a huge deal. There are no wires sticking out through the skin and nothing anchored to the bone. That means less irritation, fewer complications, and much cleaner brain signals over time. Now here is where things get really impressive. That single chip holds around 65,000 microscopic electrodes. These electrodes listen to the electrical activity of neurons across a wide area of the brain. At the same time, the system can record over 1,000 channels at once and send gentle electrical signals back through more than 16,000 channels. That level of detail and precision is something we have never really had before. The chip itself does not need a bulky implant for power. Instead, it connects wirelessly to a small external unit that could be worn like a headband or even hidden in a cap. This unit powers the chip and moves data at speeds up to 100 megabits per second, which is incredibly fast for a brain implant. From there, the information can be sent straight to a phone or computer using Wi-Fi. What makes this even more amazing is that all the electronics are built directly into the chip. It has amplifiers to boost weak brain signals, converters to turn those signals into digital data, wireless transmitters, and power management circuits, all packed into a space smaller than a grain of rice. This is only possible because of major advances in semiconductor technology. The electrodes pick up signals that represent movement plans, sensory input, and even intentions. When those signals are processed using artificial intelligence, they can be turned into real actions. That could mean moving a cursor on a screen, typing words just by thinking them, or controlling external devices without lifting a finger. Early tests in animals showed that the implant could record strong and stable signals from areas of the brain responsible for movement and vision over long periods. Short-term recordings during human surgical procedures also delivered exactly what researchers hoped to see. Full human trials are planned next, with the first focus on people affected by locked-in syndrome, ALS, spinal cord injuries, strokes, or severe epilepsy. With this much high-quality data flowing in real time, the possibilities start to feel endless. More precise seizure control, restored speech, and regained movement through neuroprosthetics all move closer to reality. And if you really let your imagination run, you can start to see a future where brains connect directly to AI systems, where thoughts become messages and machines respond instantly. It sounds wild, but with technology like this, that future suddenly feels a lot closer than we ever expected.